the next question we ask ourselves is, what is the derivative of logarithmic functions? So a couple videos ago, we talked a lot about what's the derivative of e to the x. Also, you might have been wondering, well, what's the derivative of, say, 3 to the x or 10 to the x? We didn't talk about that. But basically, we're going to come back to that later. The generalized derivative of any exponential. But really, we started with e because it was the easiest derivative there is. The derivative of e to the x is always just equal to itself. ln is not quite so easy, and what I wanted to get to in this video is what is the derivative of the natural log. Again, it's much easier and simpler than the generalized derivative. Like if you wonder what's the derivative of log base 10 or log base 2, we're going to get to that later. But we'll start with the base case. Again, e is easier. Not coincidentally, it just starts with e, because it's just that very special number that is nice in calculus. But basically, another way to find derivatives sometimes is by using what's called implicit differentiation, which is something we have not done in this class, but let's kind of get into that in this video. So, like, instead of thinking about it as a function, we could change it to an equation. Let's say that our equation is y is equal to the natural log of x, which is synonymous to the function we're trying to find the derivative of. Like, one of the things we could do is, since this is a logarithmic function, we could change it to an exponential function by definition, right? Because like a logarithm function, this is also equivalent way of saying, well, this is log base e of x. And by definition, let's go back to that from a few pages ago. The definition of a log function is a log function can always be changed to an exponential by swapping the location of x and y. Because that's the whole point of a logarithmic function, is to be the inverse of an exponential. But essentially, by the definition of log, this is equivalent to the equation e to the y is equal to x. Like, I swap the location of x and y and I change it to an exponential. This is always what a logarithm means. Or you could think about it the way we were just talking about in our equations video, where if I want to cancel out ln, I could apply e to both sides. E to the y is equal to e to the ln x. And e to the ln will cancel, leaving with x is equal to e to the y. So essentially, these are equivalent expressions. That's always what a log does, is e to what power gives me x. That's exactly what this says. E to what power gives me x. Anyways, what is the point, and how does this have anything to do with the derivative? Well, if this equation, since we know the derivative of e to the x, we can actually use this to help figure out what the derivative of ln x is. This is what's referred to as implicit differentiation. Or another way of saying is, what if I were to just take the derivative of both sides? Let's say I was to do d dx of the left-hand side and take the derivative of the right-hand side as well. Now, this is we've never done this before, but this is something that is there's some issues with doing this sometimes, but in general, you could think, well, if the equations are equal, that means that both the left and the right-hand side are the same exact thing, then their slopes should be the same things as well. Again, that works only for differentiable functions and times where this works, but in this case, both of these functions are differentiable, so it should be fine. But on the left-hand side, we're wondering, well, what is the derivative of x? That's just 1. On the right-hand side, we have the derivative of e to the y. Well, we know the derivative of e to the x is e to the x. But notice here, y is ln of x. So what we could imagine is that this technically has some compound meaning, but in this case, we would need to use the chain rule, because the derivative of e to the x is e to the x, but the derivative of e to something else is, well, equal to itself times the derivative of the inside. And since y is just the natural log of x, we could substitute that in. D dx of the natural log of x. And this would leave us with this sort of strange equation. But and notice what this, why am I doing all this and why does this help me? Notice what appears here is the derivative of ln x. This is actually exactly what I'm trying to figure out. And in this equation, if I were to divide both sides by e to the y, this would leave me with 1 divided by e to the y. And notice that e to the y is equal to x by definition based on our original function. So making that change, the derivative of the natural log of x is equal to 1 divided by x. And that might have seemed like, I don't know if that made sense, but might have seemed a little bit like mathematical trickery, but this is one of the ways you can figure out the derivative of the natural log of x. And it turns out it's actually a pretty simple function, the reciprocal function, something that if you would guess at random what the derivative would be, you probably would never guess this to be the case, but it ends up being a very simple, very interesting derivative. Or again, you could say that's x to the minus 1 power. Turns out it's actually a power function with a very specific power. And one of the things I said in class before is derivatives in calculus to me is a very interesting subject, because you often find connections between functions that you would never have expected to have some sort of connection together. And this actually unites an algebraic equation to a logarithmic exponential idea, and the fact that the derivatives of ln is equal to 1 over x is a very, very interesting fact, which actually creates a lot of interesting other ideas, which we're not going to get into in this class, but there's a lot of interesting math that comes from this sort of connection. But anyways, summary of this video is the derivative of the natural log function is 1 over x. Very simple, very interesting. And another thing to mention about this is, since the domain of natural log is only 0 to infinity, negatives do not work in here. Same applies to its derivative. Even though this derivative is defined for negatives, it does not work for 0, and this only applies to the positive side.